Okay, good morning. So, hope everybody's doing well. Um, Today we're going to talk about energy conservation. So, hopefully we'll work through some problems and hopefully that'll help you um, with the homework, help in terms of just building up your toolbox for solving different kinds of problems. We'll also make some connections with calculus, basically these a couple things that we So a couple things where we've connected uh, derivatives and integration to um, uh, what we're talking about in this section, which is energy and energy conservation. So how can they start a test during another class time? Huh. Yeah, we can chat about that, Sean. Um, yeah, before we get into the problems, let's just give you our context where we were coming from. So last time we basically introduced some ideas, but we didn't have a chance to practice them. I'm starting to have some problems with the pen. I got new batteries for my stuff, so it seems to be working better. But recall we had been looking at connection between potential energy. So let's just recap here. Potential energy being the negative integral of force. Actually, I should say this is the potential energy is the negative work done by a force, for example, gravity or a spring or something. It's got to be a conservative force. And so that's defined as the negative integral of that force. Um, and we had looked at a couple examples where we worked this out. The most significant ones being gravity. They start at the Or yeah, or maybe before we, or I don't quite follow. What do you mean they start at? Oh, do they start the class at 11:50? You mean they start their class earlier than the class is supposed to start, or something? Yeah. What's the? Yeah, they're not supposed to do that. They should only be during the time um, when their class is. So, and I wouldn't, I totally understand the temptation to kind of stretch things out, and I'm trying to be better about that myself, or where we don't run over. Um, but if they're giving you a test and you have to be there, that doesn't work really. Ah, okay. Yeah, see, they're not supposed to do that. Uh, yeah, we should probably inquire about that. I can make some inquiries. Well, for you guys, I mean, yeah, so I mean, but that's not how it should go. They should make it so that you don't have to overlap with the other classes. So for us, it's not a huge deal, right? Because don't feel like you need to watch live, right? You can always jump out and then do what you got to do, and then come back and catch the end of our stream. So catch the recording. Um, so I don't want you to ever feel like you're putting one class, like you have to sacrifice one class for another. So, and I got into trouble for doing that by having one stream, so now we're doing two. Um, and but yeah, your other courses, they definitely should not be having time that overlaps with other classes. So, for the time being, you can just jump out of our stream and take care of what you got to take care of. But you also need that space. I mean, you're supposed to have space in between so you can kind of catch your breath, go to the bathroom, take like a minute to, think of, go from thinking about one subject to thinking about another. So, and yeah, we got to be better about that. I will. Yeah, how about if this is, so it sounds like this is maybe an issue for a fair number of people. If this is an issue for you, why don't you shoot me an email and then I'll make some inquiries. I'm not gonna I'm not gonna say like who's inquiring or anything. It's just that's not really appropriate. Um, so yeah, send me an email, and I will I'll look into it and hopefully we can get that straightened out. They probably just don't know the policy because with it being online, it's really easy to kind of like, wow, why don't we do this and why don't we do this? But it shouldn't be overlapping with your other course obligations. Okay. Anywho, uh, to the physics at hand, we are talking about energy conservation. We hadn't looked at any problems so far, so we're going to do that today. To kind of recap, we had made a couple connections that are very calculus based. So speaking of math, and the issue was we had connected the potential energy, and I would mention also that we'll use the letter U to represent this as well, kind of interchangeably. I think PE is maybe a little more clear. Um, let's see. I see. I see. Um, and we had connected this with the negative work, and this was basically the work energy theorem that we had talked about at the end of the last chapter. And we had looked at a couple sources of this, so you could find the change in potential energy due to gravity, which is given by simply mg, the change in y, really. And we'd also found the potential energy stored in a spring, which was 1/2 m, or not m, sorry, 1/2 kx squared. Um, and we had also last time we talked a little bit about kinetic energy. So the other ingredient that sort of goes along with this is kinetic energy, and that's given by 1/2 mv squared. So these are kind of the ingredients that we need to talk about energy conservation. And then the complementary math statement that we had made was, well, what if you're given the potential energy and you want to find the force? You can imagine taking a derivative of this whole situation. And so the other relationship that we had was the fact that the force was given by the derivative of the potential energy, the negative derivative of potential energy. And so the first thing I want us to do is to look at a couple of basically math problems. I suspect you'll have sort of seen problems like this, really similar to this, in a math context before, but we're actually talking about work. We're talking about forces, and then we'll look at a couple energy conservation problems. So let's see. The first question that I want to look at is this one. Oops. So basically, so this is an excuse for us to exercise some math, make some connections with what you know from calculus. And so if we have a potential energy that's given by this expression, negative ax over b squared plus x squared, where a and b are constants, we want to find the force as a function of x. To do this, this is direct application of this expression that I have right up here. So the force is going to be the negative derivative of this potential energy expression. And so we need to be able to take the derivative of a quotient. So this is an excuse to exercise, brush off the quotient rule. And there's different ways that you can do this. I'm going to take the derivative, and then we'll apply the negative sign. So to take the derivative of this, it's kind of cheesy, but how I remember this anyway is if you have a quotient, it's going to be low d high, so b squared plus x squared. The derivative of negative ax with respect to x will just be a factor of negative a minus high d low. So the derivative of this b squared plus x squared would give you just a factor of 2x because the b is constant, remember. So 2x all over the square of what's below. So all over the square of b squared plus x squared. So low d high minus high d low, all over the square of what's below. That's how I remember it. Oh, square of what's below. So it's cheesy. I don't know. You may have a different way of memorizing it, but that's the skill that we're exercising here is being able to take a derivative of a quotient. And then we can recognize this simplifies a little bit. We'll have, so if we distribute our pieces here, we would have a negative a b squared, a negative a x squared, and then this would be a positive 2a x squared. Squared all over that denominator. And we can see this, these two pieces can be combined. So this would be negative ab squared minus, or rather plus ax squared all over b squared plus x squared quantity squared. And this would be what we would have, but recall, this is the negative derivative, so we have to keep that. So this is the derivative. But we want the negative of that would give us the force. So the force would be, and we can factor out an a here, multiply this by a factor of -1. So that would become a times b squared minus x squared over b squared plus x squared quantity squared. So this would be an example of computing a force by taking a derivative of a potential energy and a negative derivative of the potential energy. So in terms of what you know about calc, is this you're pretty comfortable with this? I suspect you're able to look at quotients, etc. Thoughts? Good, bad, ugly? Thumbs up, thumbs down. Weird emoji of your choice. It's okay. It's good. It's okay, too, if this is new. So tell you what, if this is if you're looking at this and you're like, this is a little bit unfamiliar, I don't feel comfortable with this, that's okay. Let me know. We can talk about calc ideas that you need offline. So, well, not offline, but not during the lecture. We can get you up to speed. Sort of. We took the derivative. So recall, if we're calculating work, you integrate the force, right? So this is sort of like taking the derivative of potential energy, which is similar to work, not exactly, but we take the derivative of the potential energy, that gives us the force. and then I guess one detail here, technically this would be, it's kind of implied that this would be in the I hat direction. Because recall, we've gone from a energy potential energy scalar to a force, which is a vector. So really, this would have some direction about it. Would have a direction associated with it. Actually, but we're being a little fast and loose with the incorporating that. So this is an example of going from energy to force. Let's exercise also the other kind of calculus connection that we're concerned with, which was to go from a force to energy. And to do that, let me give you another example problem. One second here. So the second question is this guy. So we have a particle constrained to move in one dimension is subject to the force f of x that varies with position x as f of x equals a sine kx in the I hat direction, where a and k are constants. So the question is, what is the potential energy function u of x if we take u being equal to 0 at the point x equals 0? So for this situation, we need to do the opposite. So it's more similar to calculating work. In fact, it is. So for a conservative force, recall that the change in potential energy, and actually, let me just use, I think PE is more clear. The change in potential energy is going to be the negative work done by this force, which is the negative integral of f dot dl. Now, notice we are assuming basically, although technically it's the dot product, we're assuming that our f of x and our dl are aligned. In other words, that the f dot dl becomes f dl, right? So technically the f dot dl would be the more correct definition, or sort of the more complete definition. But we're making the assumption that these are aligned, and so we just need to integrate f of x dx. Okay? So let's do that. So what does this look like? We just need to integrate the function a sine kx dx. Let me try and improve my penmanship here. A sine of kx dx. So the a is constant. We can pull that out. Why don't we just do that for completeness here? So we need, in other words, we need to integrate this sine of kx. And the integral of sine of kx is going to be what? Yeah, what's the integral of sine? What do you guys think? Yeah, it's going to be cosine. Cosine. So let's straighten out cosine versus negative cosine. So it's going to be negative cosine. So we'll have negative a times negative cosine of kx. And then we're also going to have a factor of 1 over k in here. And so I think, well, and technically this will have a plus c associated with it, right? If we're talking about an indefinite integral. So, and then the way that you can check yourself is, or check your work is, let's take the derivative of this, i.e. let's go back to here. The derivative of cosine would be negative sine, so we would have negative, here, let's just write it like this. If we do the derivative of this, if we just undo our work, we can check ourselves really quickly. So the derivative of negative cosine would be negative sine. So negative times a negative, right? And then we would also pick up a factor of the derivative of the argument here. So we'd pick up a factor of k. So in other words, our k's would cancel, our negative signs would cancel, and we would recover our sine kx. And that's what we started with. So it's a way, if ever you're like, man, I can't remember exactly if it's positive or if it's negative or whatever, I find that I remember the derivative better. So you can always kind of check yourself. It's got to all be consistent. So, in other words, the integral here would be a cosine of kx over k plus c. But we also have this boundary condition. So, in order, so this is, our potential energy, but it's in terms of this constant. So in other words, we need to figure out what this constant is. And in order for the potential energy at 0 to equal 0, what needs to happen? Well, cosine kx is going to become cosine of k times 0 over k. So in other words, cosine of 0 is going to turn into 1. So we're going to have a over k plus c has to equal 0. The only way that that can happen is if c equals negative a over k. So this boundary condition lets us straighten out what the constant is, pin down what the constant is. And so when we apply that, the potential energy, the complete and correct expression is going to be a cosine kx over k minus a over k. Okay. So this is an example now of we've gone from a force to an energy. How do you guys feel about that? Are you comfortable working with sines and cosines? So I would just make a general comment here. I think one of the things, my suspicion is if you haven't done a lot of integration and you see us do, pepper in some integrals, some calculus into class, and you might think like, oh man, do I have to know like every function under the sun and how to integrate it and everything? But I want to try and put you at ease a little bit and just say that, you're not going to know how to have to integrate all different kinds of functions. We're going to build this up in stages. You'll look at more complicated functions in Physics 2, 2021. For now, for our purposes, for 2011, for PH2011, Really, the functions that are going to get you 90% of the way are x to the n, cosine x, or cosine theta, sine theta. Stuff like that. Basically, your powers and sines and cosines. That'll get you like 90% of what you're going to need. So I approach this like a physicist often approaches math. We're going to use, we're going to know the stuff that we need in order to solve problems. And so if there's, in other words, I'm not going to like spring integral problems on you. It's going to be functions that are based in what we're looking at. So, yeah, it should be. Hopefully, it's familiar, and if it's not familiar, you can see how it kind of fits in, and it fits in with your math classes that you must be taking at about the same time. In fact, literally at the same time, apparently. So yeah, how about if you're okay, give me give me an emoji or a thumbs up or something, and if you're not, this would be a good time to ask questions about calc, about kind of what you might be expected to be able to do, etc. So questions? Yeah, so a lot of math, well, a lot of times in physics, the way that we approach math is we check and see if the answer works, right? So we'll talk about that with regards to like a differential equation. So you know what's a great way to solve differential equations? To know what the answer is and to check it and make sure that it works, right? So that's sometimes how we, as physicists, approach math. You're good to go? Okay, so we can. How's everybody else doing? Why don't you just give me a random emoji? How about? And then we'll just to kind of gauge if people are doing okay and are paying attention. Man, I can't. All right. Okay. Cool. There's some good ones in there. Some social distancing. The cough into the sleeve is amusing. Uh, I don't even know what that one is. Uh, so back to energy conservation. Let's look at a couple problems. In lab yesterday, we talked about what energy conservation is. It's it's a pretty straightforward idea. I suspect that if you've taken any physics before, you have encountered this idea. And what we're going to talk about today is basically the situation where uh, the energy that you start with has to equal the energy that you end with. So energy initial is going to equal energy final. And we're going to limit ourselves to discussion of kinetic energy plus potential energy equaling kinetic energy plus potential energy final. And this Ke plus Pe, this is known as mechanical energy. And this is the, we can write down what this is, not to beat this to death, but the kinetic energy being 1/2 mv squared, and then potential energy being things like gravity, mgh, or 1/2 kx squared if we're talking about a spring. And we'll look at some problems for both. Yeah, so this is basically getting into sections 8.3 and 8.4. And we'll kind of foreshadow what we're going to do in the section after, tomorrow and the sections after that at the end. But to start with, we're just considering situations where there isn't any loss. We can account for everything in terms of kinetic and potential energy. So to start, let's look at a real simple problem. This one here. So, and this is actually a problem that we've solved before. So I like this problem because it's a good example of how the more physics you learn, not only will you be able to solve different kinds of problems, you'll be able to solve the same problem in different ways. So we have seen this in chapter 2. With regards to kinematics, we could solve this, right? So now we're going to solve this in a different way with conservation of energy. After a particularly trying experience with MS Excel, a student decides to drop their computer out of the window of the Lock Hall Lounge. The lounge is on the 12th floor, and each floor is approximately 4 meters in height. The computer has a mass of 1 kilogram. So breaking this down, we want to find the potential energy the moment before the computer is dropped. We want to find the kinetic energy immediately before it hits the ground, and we can back out the extract the speed of the computer before it hits the ground. Yeah, right. So, we'll draw ourselves a little cartoon. What do we need? We need to know. We need to know how high this is. This brings up an issue that I want to mention, which is in terms of potential energy. It's kind of arbitrary where you put your coordinate system. Okay, so you can put it wherever you want. You could put your coordinate system here, and then when you go to do the calculations, you would find the initial potential energy would have this height, but there would also be a final potential energy that would correspond to, oh, sorry, not that height, but this height, and it would be negative. You will find working problems that it's often, it simplifies things, and it's often logical to put it so that your coordinate system, so that one of your potential energies will be 0. So what I mean is if I put our coordinate system at the ground, when you hit the ground, you have no height. So in that situation, or at that point, you won't have any potential energy anymore. Yeah, so just to review, or there's a question here about, this question feels personal. A little bit. I've considered it. I gave it some thought. Yeah, in terms of kinetic energy and potential energy, for this, we're going to be talking about 1/2 mv squared and mgh respectively, and I will fold these in as we go. So don't worry if they scroll out of the picture for the moment. So the general framework that you're going to use to approach these problems, and I think this will become comfortable for you, just like I hope setting up problems with Newton's laws became comfortable. You'd sum your forces and look for how that corresponds to how that corresponds to mass times acceleration. For this situation, the starting point is energy conservation. So in other words, the energy initial is going to have to equal the energy final. And we're talking about mechanical energy, so we're only concerned with kinetic and potential. And so the question is, we can set this up in such a way that, let's see, so we need the height. It's going to be 4 meters times 12 floors. So if the object starts here, we're dropping it. If we're dropping it, there's no initial velocity, so that object will not have any initial kinetic energy. And then when we look at, right before it gets to the ground, it's going to be moving, but it's going to have no height anymore. And so that means it would have no potential energy. And so then we can break out these pieces. So the potential energy initial is going to be the mass times gravity times this height. So if we put in our numbers, what were the numbers? We had a mass of 1 kilogram. Gravity, of course, is 9.8. And a height of 48 meters. We would find that this is 470 joules. And then if we look at the second part, the kinetic energy. So this we can relate to our, not kinetic energy, initial, sorry. This we can relate to our energy conservation expression. We know that the kinetic energy final is going to be equal to the potential energy initial. So this is going to have the same size. This will also be 470 joules. Okay. And then the last bit, what's the speed going to be? Well, we can set this up a couple different ways. I mean, one way to do this would be to say, okay, the kinetic energy final equals 1/2 mv final squared. That's going to equal this 470 joules. So we could solve this expression for v final. So we would get 2 times 470 divided by 1 kilogram. And then we would have to take a square root. Alternatively, we could do this like, we know that our kinetic energy 1/2 mv final squared is going to equal the potential energy initial. The potential energy is this. So this would equal, in other words, mgh. Now, if we do it this way, the mass cancels, and we could find that v is just going to be square root of 2gh. Either way, we run the numbers, we'll find that this velocity is 30.7 meters per second. Okay, so this is a very simple example. We're converting gravitational potential energy into kinetic energy. Let's see. So yeah, hopefully, well, I suspect that if you've seen any physics before, you've encountered and you've dealt with energy conservation. This is kind of the simplest problems that we can break down. So how does this is this pretty come across as pretty straightforward, pretty logical, or what do you think? Thoughts? Yeah, familiar? Yeah, that's what students were saying this morning too. So, and it's okay if it's not familiar. If this is new to you, it's all right. We'll get you up to speed. Yeah, it's almost too easy, right? So this is kind of the 0th example. Like, we'll look at a more complicated one next. And I would say, tongue in cheek. This is tongue in cheek, of course, but isn't it kind of sweet that we all have the same? We all have computers, because man, this online situation would be really tough if everybody, like if you didn't have a nice machine. So I don't know. kind of reconsidering my Excel hate. It's been really great having having a machine from school to be able to communicate with and stuff. So anyway, that's kind of an aside. Let's look at a harder problem. Yeah, we have to look at a harder one. That's started about as simple as we can get. So we're going to look at one that involves springs. This will be useful for your homework, and it's also just a little more interesting. So this question involves two kinds of potential energy. So let me read you the question. A ball of mass m equals 2.6 kilograms is dropped from rest and falls a vertical distance h equals 55 centimeters, striking a vertically coiled spring, which it compresses by an amount 15 centimeters, and determine the spring stiffness constant, and assume the spring has negligible mass and ignore air resistance, and measure all distances from the point where the ball touches the uncompressed spring. So in other words, it's telling us explicitly to have our coordinate system centered here. And what are we trying to find? We want to know what K is. What is K? Our spring constant. So remember, this is the spring constant that appears in the spring force, negative Kx, as well as our potential energy due to a spring, 1/2 Kx squared. Okay, so I think it's useful to basically set this one up in kind of stages, so you can see. So we can convert our initial. So let's break it down basically into 3 steps, so you can just kind of see the whole picture, and then we can go connect from 1 to 3. So the first step, we're going to see the potential energy plus, sorry. Come on, wait a second. What is going on? The potential energy plus kinetic energy initial, or at 1, let me call it initial at 1, is going to equal the potential energy plus kinetic energy at 2. Okay. So, and notice if we set it up this way, and bear in mind our coordinate system is set up so that at 2, right before the thing hits the spring, the height will be y equals 0. So if that's the case, there will not be any potential energy anymore at 2. And using the same kind of logic, if we look at the potential energy, and if we're starting from rest, then the kinetic energy initial is going to be 0. So in other words, we've made a statement that the potential energy at 1 is going to equal the kinetic energy at 2. Okay, so let's connect the dots. Now, if we look at 2, we could say the potential energy plus kinetic energy at 2. Now, I'm just being really, kind of filling in both potential and kinetic, even though we know that at 2 there isn't any potential energy. But just for completeness, just to reinforce that it's good procedure to kind of lay out all your pieces, I'm writing it down anyway. And then this is going to equal the potential energy at 3 plus the kinetic energy at 3. Okay, so now notice once we get to the bottom here, the thing is no longer going to be moving. So the kinetic energy at 3 will also be 0. Now, okay, so this allows us to connect the initial potential energy to the kinetic energy and in the middle, and to connect that to the potential energy at the bottom at 3. So we could also write this as, potential energy 1 is going to equal kinetic energy 2 is going to equal potential energy 3. So really, we're interested in the spring constant, so we need to see what's inside here. So we don't actually have to calculate the intermediate velocity. So let's table that issue and come back to that, and just connect the initial potential energy to the potential energy at 3. Now, what makes this question a little more complicated is the fact that we have two different kinds of potential energy. So initially, we just have the one. We have gravity. We're going to have mgh. That's going to equal the part that's stored by the spring. So 1/2 k, and the x in this case is going to be negative capital Y. So that's, consider that's this squared. Now, notice there's also a gravitational piece. We're also going down here. So there's also a factor of mg negative y due to gravity, or due to the fact that it's below 0, where we've set our y equals 0. Now, what that means is that gravity is to say that you have negative potential energy due to gravity is it's doing work on it. Okay, it's adding. And so we now have an expression that connects the initial height and the final position. Notice the the potential energy stored in the spring doesn't care about the sign of y, but the gravitational potential energy does. And so we can then solve this situation for y, for k. So we would have mgh plus mgy is going to equal 1/2 k y squared. And then we could solve for k. So k is going to be equal to 2. We'll pick up a factor of 2. We could factor out the mg that's common to these. That, and we could then divide by our factor of y squared. And let's put in our numbers. So the mass was, let's see, 2.6 kilograms. The gravity, of course, 9.8. Our height, let's see, we have 0.55 meters plus 0.15 meters. And then this is all divided by 0.15 squared. We crunch the numbers. This is going to give us k equals 1590. And the units, remember the units for this are newtons per meter. And you can remember that by noting that the spring force has to equal negative kx. So in other words, if you multiply k by a distance, you need to get a force. So newtons per meter times meters will give you a force. So we found k. So one detail that I would mention is this choice of coordinate system. We did this here because it makes things convenient. You could, for example, put the coordinate system down here. Now, if you do that, well, this will become a little more complicated, because notice when you go to 2, there will be potential energy still. So this choice of putting this in the middle was strategic. It just simplifies the problem a little bit. And really the most common example of this is if you're looking at like a gravitational situation. You you would often put the coordinate system at the ground, because then your other term will be 0. Let's see. Why did you pick mgy for PE3? So that is the piece that's due to gravity. I think is what we're, or I think that is what you're asking about, Evan. So this potential energy 3 is really, it's both of these pieces. There's the part that's due to the spring, and then there's the part that's due to gravity, but relative to 0, that's negative potential energy. It's below 0, so that part will be negative. Maybe another way to think about this is that you can't have a change in height without a change in potential energy. So there has to be a gravitational piece associated with that. I don't know if that answers your question exactly, Evan, but so one other detail, and then I will let you go. I was just harping on trying to be better about keeping time. Let's see, if the spring had been pulled, mg would not have been considered in potential energy, right? I'm not quite sure what you mean. So one detail before, I don't want to overrun our time too much. The other thing that we could do is we could pick out what the kinetic energy at 2 is by equating mgh to 1/2 mv squared. These m's would cancel. The v would be simply root 2gh, which would be root 2 9.8 times r 0.55. And when you crunch that, you would get 3.3 meters per second. But notice we didn't actually need that number in order to solve the problem. But that would be an additional thing we could look at. Let's see. Still not sure where the right side of that equation is coming from. So those, well, there's two potential energy contributions. There's the part that's stored in the spring, which is 1/2 kx squared. So remember, energy stored in a spring is 1/2 kx squared. And in this case, the distance we're stretching the spring, we're compressing it over the capital Y. And then there's also the piece that's due to gravity because we're going up and down, right? So, what might be helpful is to think about, suppose there's no spring anymore, right? Consider, though, if we just had y equals 0, and you had an object that fell a distance negative capital Y, the change in potential energy that would be due to that would be mg times the change in height. Now notice, if our 0 is here, the change in potential energy in this situation with no spring would just be negative, well, it would be mg negative y. Okay. Now this problem is exactly the same, except we also have a spring here. So we would have this plus the 1/2 ky, capital Y squared piece. Right? You can't have this thing moving up and down without a change in the potential energy due to gravity. But that's what makes this question a little more tricky, because we have to deal with both kinds of potential energy. So it sounds like some folks are pressed for time. You have your math exam. Don't let me keep you from that. Next time we're going to consider what if mechanical energy is not conserved. So basically, in this situation, the potential energy initial plus kinetic energy initial is going to be, when we equate that with the potential energy final plus kinetic energy final, if this mechanical energy is greater than this mechanical energy, then there must be some work that's done by non-conservative forces, i.e. friction, etc. So we'll look at some examples with that. But this idea is helpful with the homework. So if you're chugging on the homework, it's a pretty simple idea. Basically, if there's energy missing, mechanical energy missing, it's gone into something non-conservative, such as friction. So you can use this idea to calculate work done by friction. Or if you know the work that's done by friction, you can calculate like the kinetic energy or the speed or the potential energy, etc. Questions? Oh, yeah, I saw the. Did you watch the video of the UFO stuff? It's pretty weird. It's like X-Files and whatnot. It's pretty neat that they released that stuff. So what do you think? So yeah, read the rest of chapter 8. And then we'll consider situations where we have work done by non-conservative forces such as friction next time. So let's see. Evan, are you satisfied with that regarding the potential energy due to both of those contributions? Hey, Anthony, why don't you find that story that you're talking about and post it in like the random channel on Teams? It's kind of an interesting. It's a nice distraction. It doesn't involve COVID. Post it on Teams and people can see what you're talking about. Yeah, Anthony, would you do that, Anthony? Post it in there, and then these guys can see what you're talking about. Um, um, with regards to energy conservation, does anybody have any questions? Uh, Super, thanks, man. Any questions? Are you good to go? This should give you should help for a chunk of the homework, and then we'll talk about the non-conservative case tomorrow. So, okay, well, like I said, I'm trying to get better at not stepping on your other classes, so I will sign off here. If you have any other questions, shoot me an email, etc. We'll go from there. So have an excellent day. We'll see you tomorrow. You have questions on aliens.